Hi guys, greetings for the day. Hello, I'm Shantanu. Welcome to my project presentation for project progress presentation for the research project part B. My topic is learning from imbalanced data for computer vision models, and I'm working with Professor Xinyu Zhang on the same. So just to get started off, quick refresher would be the dataset that I'm using. I have chosen the Cypher10 benchmark image dataset with the 10 categories that it has. And in order to represent a class imbalance and to implement it, I have created a multi-class long-tailed version of the training dataset with exponential decay, as you can see over here. The numbers are skewed towards the right, the graph, whilst keeping the testing set balanced, so evaluation is fair. Coming on to the work that has been done until now. There's basically broadly two ways of mitigating through the data and class imbalance issue. The first way would be modifying loss functions. This would be an algorithm level strategy. The second would be data level strategy, where you're playing with the data itself rather than the algorithm. And I've also used combinations of these two paired up with ResNet models and a basic CNN model to see how it works. So to start off with, I've used focal loss, which upweighs the minority class examples to focus learning where the errors persist, basically on the tail class observations, followed by a class balance loss, which reweights samples inversely by effective class frequency. And then I have also used LDAM, which is label distribution aware margin. So what this does is, this one's actually a good one. This one applies a larger decision boundary or decision margins for rare classes. And coming to the data level strategies, I've used random oversampling or SMOT, which increases the minority presence. Now this reduces bias, but the overfitting dramatically increases, to be honest, because you aren't quite seeing any sort of new data with oversampling. Coming to mix-up augmentation, what it does is blends images across different classes to encourage smoother boundaries. And also class aware sampling, what this does is it ensures equal class representation within each batch, which improves convergence stability. Now coming to the results of these techniques is that we do see quite an increase in performance on the long tail data set, but the values, the recall values and the accuracy values for tail classes are still quite suboptimal. Fair to say that quite unacceptable in some cases. So moving on. Now vision transformers are one of the most trending ones to go with right now. So transformers usually show very strong performances with image classifications due to their global attention and long-range feature capture. I've implemented the Vision Transformer VIT on a long-tail Cypher10 on the long-tail Cypher10 dataset, and what I have found out is that this does achieve slightly higher accuracy numbers and better recall values than the CNNs and the ResNet models that we've tried out before, but the improvement is almost negligible. It's like a 3% improvement overall, and the numbers are still biased towards the head classes and the tail classes performing quite poorly. Now the reason for this is that transformers are quite data hungry and they require large data sets, or if they're balanced, that's awesome, but if the tail class still has a lot of samples, the transformers would still perform decently well. That wasn't the case with us. And like I said, the lack of diversity in the minority sample uh, doesn't help us too much. Coming to the results so far, this is a result of the resonant model along with the focal loss function that was integrated. This one's just for an example, but most of them follow the same structure. If you look at the plots, you see that towards the left we have the two graphs. Now, the classes with the most number of samples are towards the left within these graphs. That would be airplane and automobile. Because these classes have a high number of samples, the models perform quite well on them. So you can see per class accuracy numbers are quite high for these. And as the number of samples go down, the graph tends to get skewed towards the right. Another interesting thing to look at is the misclassification. So that would be the false positives and the false negatives. So the false positives is skewed to the right. So where the tail classes are, the false positives there are quite low, and false negatives are quite high towards the tail classes as expected. You could also look at the third plot that is here. It's a comparison between all the models, and we have accuracy, macro F1, and macro recall all tied up together for each of the models. So now the first two models are on the balanced data set. The first one would be the CNN, the second one would be the resonant model. After which we have created the unbalanced data set, as in the multi-tail. We've been using the multi-tail data set, and you see all of the numbers start to plummet down quite a bit. We do see that oversampling produces decently good numbers, but this is we did address this before, because like I said, oversampling it does give you good accuracy and good numbers, but the models are to be overfitting for the most part. And now moving on, this shifts our focus a little bit towards the generative models. Now, generative models are the talk of the town, talk of everywhere, to be honest. And now that I've used different advanced data level and algorithm level techniques, such as the deep SMOT, focal loss with resonant 18, even combinations of them, we see that the minority class performances are still suboptimal, and now this is because of purely the lack of samples that we've got. The generative approach would create new synthetic data. So this would enable us to have diverse and realistic image samples to better represent the tail classes and populate them well. There's multiple models that we want to be looking into. The ones we're interested in would be the GANs and the VAEs and the diffusion models. And we've also got autoregressive and nano-banana models that we could be looking into. How this works is these models work on the imbalanced data set. We train them on them, and then they generate these images for the minority classes. This helps us get a balanced and diverse training data set, and then we evaluate the models and train the models and evaluate them further on this going ahead. Now, the thing is, before straight away going into generative models and running them, we really need to understand how each of these sub classification of these generative models, like the GANs, the WAYs, and the diffusion models work. So I'll try to explain that in short and in simple. All right, we've got the GANs to start off with. Now that stands for Generative Adversarial Network. It is not as complicated as it sounds. So how these work is that they've got two deep neural networks trained in competition. So we've got a generator that produces fake images from random noise. And the goal of the generator is to fool the discriminator into believing that the fake image is real. So the discriminator distinguishes between real and fake images. And if it says the image is fake, the image is sent back to the generator. The generator learns that. It's like a back propagation kind of a thing. The generator learns from it, makes the image slightly better, generates a new one, and sends it back into the discriminator. And once the discriminator cannot distinguish between the real and the fake image, that would count as the discriminator having been fooled. And then this image sample is added into the data set. It's quite pretty stock standard in it. Uh, Now we've got the DC GAN as well over here. The DC GAN and the class conditional GAN. These are the two models that I'd like to explore further. So the DC GAN is a baseline convolutional GAN for small images. It would fit perfect for the Cypher 10 dataset that we're working with, along with the class conditional GAN. So this would generate conditioned. The generator would be conditioned on class labels, so you can produce images of selected classes. And we've also got AC GANs and big GANs to have a look at. Moving on to the next ones, this is this version's called the diffusion model. Now we've got two examples that we're going to mainly look at: the DDPM and the DDIM. So diffusion models have a pretty simple to understand generation process. So the generation here goes about in two directions, in two phases. The first is the forward phase. So in the forward phase, we add noise to the real images, where we try to gradually destroy the structure until we've got something of this sort on the bottom right. After which, in the reverse process, we try to gradually remove the noise and to reconstruct a realistic image. Now, the realistic image would obviously slightly be different from the original image that we had, and this way we'd create a diverse amount of images. Now, something to keep in mind is that they are quite computationally intensive. But they do produce extremely high quality and diverse data sets, especially on the Cypher 10. So, the DDPM would be the base diffusion model. It stands for denoising diffusion probabilistic model. This, along with the DDIM, which is a faster version, would be the two models that I'd be looking at potentially. So next up, we've got the VAEs, which are the variational autoencoders. Now these work slightly differently, actually a lot differently. The VAEs are probabilistic generative models that learn from a compressed latent representation of data. So what happens is that the model encodes an input image into a latent vector, and these samples are then there's a latent space that is created out of this, and samples are then picked out of this and then decoded back into a reconstructed image. Now the sampling step that is here allows VAEs to generate new images that are similar to the training data. So you wouldn't get the exact same image, it would be slightly different. What it essentially does is that it encodes an input image into a latent vector and then samples from this latent space of vectors and then decodes it back. It's got multiple different types of them. So the standard VAE along with the conditional VAE, which generates images conditioned on class labels. These are the two that would be that I'd be fairly looking at. The training happens by minimizing the reconstruction loss and the KL divergence as well. It's a regularization term involved. Next up, we've got the autoregressive models. Now, how these work is that it generates images sequentially, predicting one pixel or one patch at a time. So each prediction depends on all the previously generated elements. It's a similar principle to language models that we have we've studied past in NLP by looking at the previous words in order to predict the next word. Now the issue with this is that because it goes pixel by pixel at a time or patch by patch at a time, they are very they do provide highly detailed and consistent images, but the image generation process would be very slow and extremely computationally heavy. So there are some examples here with Pixel RNN or CNN along with Image GPT. So if possible, if these models can run at a decent enough pace, then these would be considered, but these aren't the ideal ones for us to look at. Coming to the final slide of this, we've got something that's very new. This is one of Google's newest model. It's called the Nano Banana model. It's a lightweight generative model which is optimized for speed and efficiency. So this model would also be looked at because the Nano Banana model is known for producing the best quality of images. So we could use I would be using this as a benchmark to generate images, and then to compare my generated images along with the Nano Banana generated images. Optionally, there's also hybrid models of combining GANs and VAEs, but these would be extremely difficult to implement, but these are options to at least be researched. Here I've got a quick table that you could have a look at. It talks about the mechanism and the strengths of each of them. We've discussed about this. And yep, that brings us to the conclusion. So as of now, I have implemented a diffusion model, the DDPM model. Although I haven't been too successful on how clear of an image I've been able to generate with it, but the upcoming focus is to go for class conditional synthesis using GANs, VAEs, and diffusion models, and optionally hybrid models as well to improve minority class representation. Thank you so much. Have a good day.